right. Actually, we're gonna be doing sketching this like today. One of the things that you have to actually learn to notice that this is actually an even function. Do you guys remember even functions? How do I know this is an even function? That wasn't part of this like question, but do you guys see that's an even function? Yeah, plug in negative x. If you square anything that's negative, it becomes positive. So it just comes back to, right? So if you plug in negative x, it will just come back to being equaling the original function. Okay. Okay, let's find the derivative to find the critical numbers. It's going to be 2x, x squared plus 4 minus x squared minus 4, 2x, like that, right? Alright, I'm going to factor out 2x right away. It's faster than expanding. That's gone. And this actually turns out to be pretty clean. Right, so we have 8 inside, so we're going to have a 16x. Okay, so what are the critical numbers here? So the only critical number here is x is equal to 0. Okay. Now, is that a local max or minimum? Again, you got to ask yourself this question: when is the derivative increasing, or when is the derivative positive? This is a very easy one, right? X squared plus 4, that's always positive. So the whole thing will be positive as long as x is positive, right? So here's 0. So if x is positive here, right? It's going to be positive here, negative here, so it's going down and up. So it's a local minimum. Local minimum. Okay, and if you want to find out the exact point, you just plug in 0 and you get -1. So 0, -1 is local minimum. Okay, let's go on to the second derivative. Okay, from here, I'm going to continue from here. Leave the 16 out at the front, and I'm going to do quotient rule one more time, so you get okay. So we get that, and minus x. You get 2x squared plus 4 chained by 2x all over x squared plus 4 to the power of 4 this time. So we can reduce a little bit. One of those gone, one gone, you get 3 here. Okay, so we get 2x times by 2x, that's 4x squared. Okay. So we have 4 minus 3x squared. Okay, so I'm going to force factor this with the square roots. There's going to be 2 minus square root 3x, 2 plus square root 3x, right? So the potential inflection points are 2 over root 3 and minus 2 over root 3. Okay. Now, I want to know, when is the second derivative positive? Now, do you see that the bottom's not going to matter? Again? Okay, so we only have to be worried about this. When is that? When is this positive? Whenever you have a negative like this, get rid of it by multiplying that bracket by -1. So you get this. This one I can just switch the order around. But I did that by multiplying the left side by -1, so I gotta multiply the other side by -1. That switches the inequality sign like this. So this tells me the second derivative, we have two inflection points, or 2 points, 2 critical values of the second derivative, is -2/√3, 2/√3, like that, right? So it's positive in between. This tells me it's positive in between the parabola, right? Between the two values. Positive, negative, negative. So are these two inflection points? Is the concavity changing as we go through this number and this number? Yes. Okay, so therefore, therefore they're both inflection points. Therefore, inflection points are at -2/√3, or plus minus. You can just say that. Okay, so that's a justification that one you need to show.